Hey, we're going to talk briefly about chemical compounds with Lewis dot structure. If we remember, a Lewis dot structure shows a total amount of valence electrons around a specific atom. We can go up to 8 valence electrons because we follow the rule of octet. So, for example, if we have the atom carbon, carbon has 4 valence electrons. We get that number because it's in the 4th column on the periodic table. Remember, when we draw our Lewis dot structures, we don't want to pair our electrons together. So if you draw carbon like this is not correct. So remember, you want to draw your carbon with the electrons individually dispersed as such. If we were to draw something like oxygen with its Lewis dot structure, you have oxygen. Oxygen is in the 6th column on the periodic table, so we're going to give it 6 dots. And we want to move in a fashion such that we have unpaired electrons. This electron right here and this electron right here is considered an unpaired electron. These are the electrons that make bonds. So if I ask you how many bonds can oxygen make, you're going to say 2 bonds because it has 2 unpaired electrons. So oxygen is trying to react or bond with 2 different elements as well. That's why when we have a compound like H2O, there are 2 things bonded to the oxygen to form the compound. Now, when we talk about doing chemical bonds with Lewis dot structures, we need to know that the element with the most unpaired electrons will be the central atom. And we'll get into that a lot more here in a second. A central atom is just, this should say unpaired. So a central atom is just a specific element in the middle of an entire compound. That's what this central atom is the middle atom. And then everything else will surround it in an even fashion. We call that molecular geometry, and we're going to talk about molecular geometry a little later this week. So the element with the most unpaired electrons, if you remember back to the previous Lewis dot structures we drew, oxygen had 2 unpaired electrons. Those were the 2 single electrons looking to make bonds. Something like carbon has 4 unpaired electrons. So our unpaired electrons are our single electrons. So let's do a couple of bonds. Let's start with the CH4. CH4 is methane gas. That's its common name or street name. You could also call it carbon tetrahydride. Those are both acceptable names for CH4. So if we start with our Lewis dot structure, we're going to start with our carbon. Carbon, we've drawn it already, has 4 valence electrons. Then we have hydrogen. Hydrogen, there are 4 hydrogens in CH4. That's that 4 beside the hydrogen right here. Also the tetra, if you're looking at the name of it. Each hydrogen has 1 valence electron. Now, the atom that's going to go in the middle of this compound is the specific atom that has the most unpaired electrons. In this case, each hydrogen has 1 unpaired electron. The carbon atom has 4 unpaired electrons. So the one with the most is going to go in the middle. So we're going to draw this carbon in the middle. And then our carbon has got its 4 valence electrons. Now, each carbon wants to make 1 bond right here, so we can bond 1 time with hydrogen here, 1 time with hydrogen here, 1 time with hydrogen here, and 1 time with hydrogen here. And if we count the total amount of valence electrons around the carbon now, it has 8, so it satisfies that octet rule. Remember, hydrogen's an exception. It only wants 2 valence electrons, and it has 2 valence electrons now with this chemical bond. So this would be the correct Lewis dot structure for methane. We talked about previously in the last unit that 2 dots can be represented by a single line. So if you draw this with a line creating the bond between carbon and hydrogen, this is also acceptable. Now we can get into this just a little further. So what we can talk about here is we can talk about the total amount of bonds that carbon's able to make. In this case, we have 4 bonded atoms, or that's 4 elements that are bonded to the carbon. It has 0 lone pairs because every single electron is bonded. If I drew 2 electrons right here, we would say carbon has 1 lone pair. But it has 0 lone pairs because these 2 dots aren't supposed to be here. And so when we add our bonded atoms with our lone pairs, we get this thing called electron domains. So if we have 4 bonded atoms and 0 lone pairs, we're going to say that there are 4 electron domains in this methane molecule. We can do another chemical compound. We can do something like NH3. This can be named as nitrogen trihydride. Nitrogen trihydride has a nitrogen molecule. Nitrogen has 5 valence electrons. So I'm going to give it 5 dots. And then there are 3 hydrogens attached. Each hydrogen has 1 valence electron. The first thing we need to decide here is we have to decide which of these atoms is going to be in the center of this chemical compound. The nitrogen has 3 unpaired electrons, right? We have this electron right here, this one, and this one. These are our 3 unpaired electrons. Unpaired. This section of nitrogen here, this is our lone pair. So it's already a pair. It doesn't want to bond. If you look at our hydrogen, we only have 1 unpaired electron in each hydrogen. The atom with the most unpaired electrons is going to go in the center. In this case, nitrogen goes in the center of the atom. And we have our 5 valence electrons. Now, each hydrogen is going to be able to connect at a specific spot that has an unpaired electron as such. So if we're looking at this compound now, nitrogen has 8 total valence electrons. Hydrogen has a total of 2 valence electrons in each location. And hydrogen wants to satisfy that with only 2. Remember, it's an exception to the rule. Nitrogen has its 8, so it's going to be happy. If we want to break this down to our total amount of bonded atoms, there are 3 atoms bonded to our nitrogen. We have hydrogen, hydrogen, and hydrogen. Those are our 3 bonded atoms. Our lone pairs around nitrogen are our electrons that are working together. Our nitrogens that are our lone pairs are the electrons around our nitrogen atom. In this case, we just have these 2 electrons right here. The other electrons are already working with our hydrogen. So this pair is going to be considered our 1 lone pair around our nitrogen atom. If we add these together, we get our total electron domains. So 3 plus 1, we have a total of 4 electron domains. An electron domain is just an area on a specific molecule where electrons are behaving. We have the bonded atoms. Our electrons are being used in chemical bonds. Our lone pairs, these are negative charges right here. So our negative charges are going to push against other negative charges when they interact with other molecules. So this would be our Lewis dot structure for nitrogen trihydride. You could also draw it if you wanted to. You could do your nitrogen with its lone pairs connected to hydrogen, hydrogen, and hydrogen like this as well. That would be fine. Because remember, 1 line equals 2 dots. The last example I want to work through is carbon dioxide, or CO2. Carbon dioxide. So carbon has a total of 4 valence electrons, we know this, and oxygen has a total of 6 valence electrons. The first question we ask ourselves is which atom is going to go in the middle, or which one has the most unpaired electrons? Oxygen, each oxygen molecule has 2 unpaired electrons. the carbon molecule or atom has 4 unpaired electrons. So our carbon is going to go in the middle with its 4 electrons. Now, if we put oxygen over here with its 6 electrons, and we can put oxygen over here, the other one with its 6 electrons, we run into a little bit of a problem. We still have some unpaired electrons, right? We've got this connection now between our oxygen and carbon and this one, but oxygen right here is unpaired. This oxygen is unpaired. This carbon is unpaired, and this carbon is unpaired. If we remember back to our types of covalent bonds and our polar and nonpolar, there were 3 kinds of covalent bonds. We had single bonds, we had double bonds, and we had triple bonds. In this case, we can make a second connection between our electrons here and here and form what's known as a double bond. So if we redraw this molecule, we have carbon. It's formed a double bond to oxygen on both sides of the molecule. Remember, each line represents a total of 2 electrons. So if this is 2 electrons, this is 2 electrons, this is 2 electrons, and this is 2 electrons, carbon still satisfies the octet rule. Carbon still has 8 valence electrons. Each oxygen molecule also satisfies the octet rule. They have 8 valence electrons. So this would be our chemical bond. We can draw these as single bonds, double bonds, or triple bonds whenever we're doing the Lewis dot structure of these molecules. If we want to break this down and look at our total bonded atoms here, we have 2 atoms bonded to our carbon. We have an oxygen here, and we have an oxygen here. It doesn't matter how many lines that we draw between the carbon and oxygen. We're just looking at the total number of elements attached to carbon. In this case, there are 2 attached to carbon. If we want to look at our lone pairs, this is a tricky one. So we always want to focus on the central atom. We can ignore the lone pairs around our oxygen molecule. We're just looking at our central atom because that's going to determine what our geometry is, which we'll talk about later this week. So if we look at our carbon, how many pairs of dots does this carbon molecule have that aren't connected to oxygen? It doesn't have any, so we'll say this has 0 lone pairs. So when we calculate our electron domains, or areas that electrons can behave, we have 2 plus 0, or 2 total domains. This is a lot less than we had with our NH3 molecule and with our CH4 molecule. So your domains can change. Usually it's going to hit 4 at the highest. Sometimes it's 2 or 3. So this is how we do Lewis dot structures with chemical compounds. You're going to have a worksheet to work on this and to get some practice just working on the Lewis dot structure portion of the worksheet.